Inside an old-growth forest, every branch and leaf competes for a fraction of the available canopy. To the eye, these overlapping layers of green are a tangle of competing growth. This environment is defined by a hard physical constraint. Space is finite. Every square inch occupied by one plant is an inch stolen from another. In this system, spatial inefficiency is a lethal error. A leaf that blocks its own neighbors or fails to find an opening loses the light it needs to survive. How does a forest coordinate this growth across millions of organisms to prevent a total collapse into spatial gridlock? The forest canopy organizes its expansion according to a rigorous mathematical proof, calculating its own survival through recursive logic. By moving past the macro level of the forest canopy, we can map the specific geometric rules that govern this growth. Survival in the wild relies on the execution of precise spatial optimization. We can see this logic in action on the face of a single sunflower, a bounded biological space where every seed must find a home. The seeds radiate from the center in spiraling patterns that correspond to the Fibonacci sequence. In this sequence, every new number is the sum of the two that came before it. 1, 1, 2, 3, 5, 8, creating boxes that expand into a logarithmic spiral. Dividing consecutive numbers produces a quotient honing in on 1.618. This golden ratio mathematically solves tightest seed packing, ensuring zero overlap or gaps. The plant grows according to a biological algorithm that builds the golden ratio to maximize its limited surface area. If we view the sunflower head as a strictly bounded mathematical set, we can apply the tools of calculus to understand why this pattern persists. The Bolzano-Weierstrass theorem states that any infinite sequence contained within a fixed boundary must eventually converge on a specific limit point. This diagram shows the theorem's core logic. As the sequence of dots multiplies within this circle, they are forced into a state of convergence at a central point. In the plant's growth cycle, the golden ratio functions as this theoretical limit point, providing a stable coordinate for every new seed to emerge. This convergence ensures that as the plant grows, every new leaf or seed is placed at a precise angle that avoids blocking the ones that came before it. Biological growth patterns closely mirror the behavior of sequence convergence, allowing the plant to navigate its physical limits. Zooming out from this mathematical limit point back to the sunflower field, we see the result of that efficiency on a massive scale. The Bolzano-Weierstrass theorem describes a logic that extends far beyond a single flower or a chalkboard. This same recursive logic dictates the branching of the trees in the canopy, allowing the forest to layer itself without choking out its own growth. This architectural logic is visible in almost every growth pattern we encounter in the wild. What looks like the chaos of the forest is a perfectly executed calculation where plants use recursive logic to achieve